Okay, hello and welcome from my side. My name is JP Lair, and I'm going to talk about the AMD compilers for the AMD Instinct accelerators. I work at the AMD ROCm compiler team, and I'm happy to talk about ROCm. So let's first look at the agenda. First of all, I'm going to explain a little bit about our compiler ecosystem, because there is sometimes a little bit of confusion there, which compilers AMD offers. And so I'm going to outline which ones we have and what targets there are. Next, I'm going to talk about the different Instinct accelerators that we have in our portfolio. And then I'm going to talk about, for the majority of this presentation actually, about OpenMP target offloading for targeting GPU accelerators. And finally, we are looking at the USM, or Unified Shared Memory mode, via zero copy. So the AMD compiler ecosystem. First off, we can think of two distinct lines of AMD hardware. One is the AMD EPYC CPU line here on the right, which is targeted by the AOCC compiler, which is AMD optimized CPU compiler. And then we have AMD, the CPU libraries, and the ZenDNN and uprof as the profiling tool. And on the left-hand side here, we have the AMD ROCm software stack. And that's the one that actually targets the heterogeneous platforms. So this one ships with HIP, which is the Heterogeneous Computing Interface for Portability. Then that supports OpenMP as well. We have machine learning frameworks as part of that software stack, the acceleration libraries. And then, of course, we have the ROCm communication libraries, or RICL. And that sort of gives you an idea that we have, on one hand, the ROCm software stack, and on the other hand, the AOCC part of the software stack. And ROCm targets offloading to GPUs, and AOCC targets best performance on CPUs. Now, looking at that a little further, how these compilers and infrastructures relate to each other, I want to have a brief look here at these compilers. So first off, our compilers are based on LLVM, and there's the upstream LLVM project, LLVM, which is the open source community-driven development. We then have merges from the development there from upstream into our internal development branch, and that then eventually gets into AOCC. We then also have another branch we have also other merges into what is called the AMD staging branch, which is the open source part, and this is eventually going into ROCm. And here we have as sort of the development compiler where we work on is AOMP, and whatever gets into AMD staging potentially makes their way into ROCm. And then to add a little more, we currently have what we call AMD trunk dev, which is not part of AMD staging, but directly based on LLVM project. And that goes into, together with some components of AMD staging, into the what's called the ATD compiler. And this is actually interesting. Oh, let me get the camera out of the way here for a second. As I mentioned, LLVM project up here is driven by the community. It's open source software. We then also have this part, which is open source software, but by AMD. So you can look at these things. The URLs actually here on the screen. They're on GitHub. And then finally, we have AOCC, which is a closed source software by AMD. And so this is how the different compilers relate to each other. So we have upstream here, which is an open source driven by the community. We have basically ROCm or components here with different flavors, which is also open source, and you can find that on GitHub. And then we have the closed source AOCC, which is here. And our LLVM Clang work actually happens here in AMD Trunk Dev. But then we also, of course, upstream our contributions to LLVM project so that the community can benefit from our development efforts. Okay. Let me get this again here. So let's talk about accelerators. Click. Here we go. So there's exciting times. We have the AMD Instinct MI300X GPU, discrete GPU. It's a pretty powerful GPU. Ships with over 300 compute units, offers 192 gigabytes of HBM3 memory, and it comes in an OAM form factor. Now, one of the things that I wanted to mention is that it supports unified shared memory via page migration over PCIe, PCI Express. However, for the discrete GPU case, that's not necessarily the typical use case, right? So here you would usually not use unified shared memory, but you would rather use optimized copy operations to move memory from your host to the GPU, keep it on the GPU, and work fully on the GPU. But we also have a different product, and that's called the AMD Instinct MI300A, and that's an APU. So that means in this product, we combine CPU cores, which we have 24 CPU cores of the Zen 4 architecture here, together with 228 CDNA3 compute units. And on top of that, there is 128 gigabytes of HBM3 memory. And the interesting part is that this actually offers unified memory, right? And it's the APU that powers El Capitan, the supercomputer. And here, there's no distinction between CPU and GPU memory. So this is the prime candidate for unified shared memory because it's actually unified memory in hardware. And so this makes it, a very good target for OpenMP's unified shared memory concept. So let's look at that more closely. So here we have an example program, this time in Fortran. And typically when you use GPUs, you have discrete GPUs. So let's look at discrete GPUs first. And we typically call this the default mode. So here we allocate some values. They are allocated on the host. And then we have this OMP target loop here with a map clause that says to from vals, which means that the runtime system will allocate space on the GPU in the HBM of the GPU large enough to fit the 1024 values that were allocated here. And then before the kernel launch, the runtime will copy the contents of vals into that newly created storage on the device. We refer this to as like devals. Then we execute the kernel on the GPU, and after the kernel completion, there's another memory copy operation that copies the contents now from the device back into the memory on the host. So that's the typical work here in default mode with the map clause and the to from specifier, which means move the data to the device before the kernel and then move it from the device after the kernel. Here, as I mentioned, the operating system allocators allocate host memory. Now let me get this briefly out of the way again. So now on GPUs, we can actually do USM mode as well, right? So we can run in unified shared memory mode on an MI300X. What we need to do is we have to add the OMP requires unified shared memory clause to our translation units. And then we do regular like allocate vals. We still have the OMP target loop map to from vals. So we don't need to change our code here, except that we have to write this unified shared memory clause here. And here, what will actually happen is that now there won't be any discrete GPU copies because the driver will actually handle the page migration. And so vals can access addresses from host memory, basically. And that will trigger a page migration to the GPU HBM memory. So still, the allocator, the OS allocator allocates host memory, so that's not different. But then accessing that address here will actually trigger a page migration to the GPU's HBM. And basically that map clause here, which in the discrete GPU case, in default mode, triggered the allocation of device memory and the copy of the contents, now just decays to passing the host pointer to the kernel. Now, on MI300A, remember, that's a unified memory system, right? There's something that we call zero copy mode. So we have the same source code example here. See. So we require unified shared memory. We allocate regular memory here. We still have the map to from clause here, and we have the kernel. Now what will happen here is that the operating system allocator will actually allocate unified memory. That means it will allocate memory on the HBM, but that HBM is shared between CPU and GPU. And so this map also just passes a pointer to the kernel, a pointer to that allocated memory over here, to the kernel. Since there is no need to either explicitly copy data to a device memory, or even do page migration from the host memory to the device memory, because it's a unified memory architecture. And so here, when we access the allocated variables here, vals, there's no page migration necessary, right? At least in the single socket example. If we allocate across multiple sockets, that's different because we still have to bring in the memory from other sockets. But that's not too uncommon if you have multiple sockets with local memory, right? And so this is a nice benefit here where you can just allocate memory on a shared HBM and you do not have to pay for potential page migrations. Okay, now let's look at the site-to-site comparison of basically that example, but this time in C, or yeah, it's C. So here on the left, we have the regular, let's say, default mode C code, where most importantly, I would say, you would have your allocation on the host, you would have the map clause that maps the data to from the device, and you have the kernel. And on the right, you add the pragma OMP requires unified shared memory clause, and you can leave out the map clause here because the runtime system will take care of the page migrations for you. Now you have to add the OMP requires unified shared memory clause in every translation unit. That's a bit tedious, but ROCm offers actually a compiler flag to do that for you, so you don't have to modify your source codes in order to benefit from that. And on the next slide, there's quite a bit of LVMIR, so the intermediate representation that the compiler will generate. And there's two differences that I think that are going to be highlighted. So without unified shared memory, on the top, we will have two entries, which is the entry name, and here an offloading struct that has pointers to some of the, let's say, metadata and regions. And with USM, we will of course still have a name, but then the struct is actually a little different, and it has less entries. Now the more interesting part, I think, is, and that's on the host side, to be clear. Now the more interesting part here is that in the target binary, if we look at these two LLVM-IR DOMs for the kernel, right? So that's the device side intermediate representation. The difference is actually 0. So the compiler generates the same LLVM-IR, independent of whether we're using unified shared memory or not. And that's cool. I think there's a little asterisk to that, which is required for the handling of globals. But if anything, I'm going to cover that a little later. All right. Now, the difference in runtime behavior, that's something interesting to look at. So this is a debug output from our runtime. And when we're not using zero copy at the top, we see that we actually allocate memory on the device here. We're then moving data to the device, from the host to the device. And then we have this part here, which is the pointer translation, basically, where when we pass in the pointer, the runtime does the translation to actually hand the device pointer to the kernel, so that that one can actually access the device memory. When we're using zero copy here at the bottom, we see that there's simply a return host pointer begin for unified shared memory. So we really just hand off the host pointer to the kernel, because we're not copying data in that case. We're just using the allocation on the HBM that was done using the regular operating system allocator. Right? So no memory allocation or copy operation is necessary. So when we're doing programming an MI300A APU with OpenMP, we do have basically a default programming mode and a unified shared memory mode. And the runtime will actually do a little magic that if you are programming in default mode, which means you do not use unified shared memory, the OpenMP clause, and you're using map clauses, but you are now running on an MI300A system that enables the driver feature for XNAC, which is the driver feature behind unified shared memory. If you do that, then our runtime will give you automatic zero copy on an MI300A. So even if you target discrete GPUs, you don't have to change the way you program. You don't have to make changes to your source code. The runtime will do the magic for you, and you will benefit from zero copy. If you, on the other hand, disable the XNAC feature in the driver, you will get your regular copy behavior, which means that you will get allocations on the device HBM and copy data. Now, if you program in unified shared memory, so that means you either add that clause or use the compiler flag to force it, or to enable it globally, let's say. If you're using the XNAC feature, you will get zero copy as well. But if you disable the XNAC feature, then the driver machinery that USM relies on goes away, and so you will receive a runtime error that tells you that this is incompatible. And so now, before jumping, we did a little bit of now performance evaluation for a quantum Monte Carlo application called QMCpack. The website is listed here. And now, before we jump to the graphs of that, I'm going to remind you that just be sure you like have this table in mind when you do that. So the performance results are for a quantum Monte Carlo production application called QMCPAC, and they are run on a single socket MI300A using zero copy and copy configurations. The objective of this analysis is first to understand whether using zero copy has a negative impact on performance, and second, to understand what are the factors that affect the performance. So let's start with this graph. It shows the ratio between copy and zero copy in the default and the USM case. On the x-axis, we have the problem size of the QMCPAC configuration. And on the y-axis, we have the ratio between copy and zero copy. When the ratio is larger than 1, it means that zero copy outperforms copy. A higher ratio means more advantage from using zero copy on the MI300A. And as you can notice on this graph, the zero copy configuration always wins over copy for the QMCPAC runs we did. A first thing to notice is that USM and default performance, when in zero copy mode, is very similar, right? These two curves are very closely together. And this is expected, as the difference between the two for QMCPAC is only the presence of the unified shared memory tag. Okay. Another aspect to notice is that the ratio becomes smaller for larger problem sizes. That is expected as well, because for larger problem sizes, we spend more time executing on the GPU instead of moving data from host and GPU specific memory. So smaller problem sizes, on the other hand, have most to gain from zero copy, as copy spends comparatively more time in moving memory than computing actually inside the kernels, right? Now, when we look at the same data, but this time we fix the problem size and we toggle the number of OpenMP threads on the host. So x-axis is now the number of threads, the number of OpenMP threads executing on the host and offloading to the same GPU. So this is, in QMCPAC, you can use multiple OpenMP host threads per MPI process. And all threads belonging to the same process launch kernels to the same GPU. So increasing the number of threads means that there are more threads contending access to the driver. And as you can see, increasing the number of host threads results in a larger advantage from zero copy compared to copy. That happens because in the copy configuration, host threads make more requests to the driver compared to zero copy. They need to ask the driver to allocate GPU-specific memory and to copy to it. So more requests translate to more waiting if you increase the number of threads actually making those requests. So in summary, zero copy is a ROCm runtime feature as compared to the unified shared memory, which is more of an OpenMP standard language concept. Zero copy enables the execution of OpenMP programs without explicit data copies in almost all cases. And the code generation is actually unaffected. The program continues to use the program can continue to use map clauses. So you can still also target discrete GPUs in a single source code. While if you enable USM mode, the code generation may be slightly different. That comes down to some register allocation specifics. There is the zero copy and USM mode both require hardware and driver support, so they may not work across all existing devices. But the ones that do not support this are out of support by now. And you can enable the zero copy feature, especially in MI300A, via environment variables on the supported devices. And USM mode, you still need to set these environment variables. But for USM mode, you also need to add the unified shared memory clause, or use the compiler flag OpenMP force USM to enable it globally for your program. And with that, I hope I gave some interesting points here, how things work, what we are supporting in AMD ROCm, and happy to see you next time.